Hi, everyone, and welcome to our regular Chance Talk, where Sam Savage and I, Alex Sidorenko, discuss interesting probability problems, interesting decisions, and share stories how we can apply quantitative risk analysis to a problem near you. Let's see if today's problem you can relate with because it's fun and you can convert it into something very practical and very useful to your day-to-day work or maybe even life. So, Sam, what do you have for
Yeah,
us today?
thanks, Alex. And by the way, folks, Alex's internet connection is none too great, so I'm just going to sort of charge ahead here. What we're going to be talking about today, actually, is Bayesian analysis, and um, poorly understood, extremely important, and I'm going to try to explain it in a way that you can all understand. Um, what we're going to start with here is a sneak preview um, of a model based on the Top Gun movie. This is a sneak preview. We're not going to publish this. We've got some exciting stuff coming up with the Military Operations Research Society that you will learn about in due course. And this is going to be part of a thing we're doing with them. But the Top Gun movie has this impossible mission where Tom Cruise has got to lead an attack that takes out a nuclear reactor before they fuel it, right? So there won't be any radioactivity problems or anything. And the mission involves a double attack. So the first attack has to destroy the armor plating protecting the reactor door or something. And then the second attack blows up the reactor. And so here we have the black attack and the blue attack. And here we have the black weapon and the blue weapon. And we can see we're going to do like 10,000 trials. And as we scroll along, we see the weapons land in different positions. Now, the weapons are laser guided weapons. They're very accurate, but there's a chance that the laser might fail. I'm just going to intentionally disable the laser on the second attack. And when I do, you can see this big dispersion ellipse of where would the weapon lie if you didn't have the laser. And the ellipse can be adjusted because some pilots are better than others, right? So here we have, two errors in the horizontal and vertical direction. See, if I reduce the vertical direction maybe to 3 meters, let's see. Oh, well, then we see the chanceometer moves and that moves. Here I'm going to undo. I'm going to go back. And the mission failed, by the way, in this case.
So, Sam, can I
And
just quickly,
yeah,
quickly say a couple of things? So, first of all, if it's too difficult for you to see, if you're watching on LinkedIn or YouTube or Twitter or Facebook, if it's too difficult, make it to full screen, and then you'll be able to see the full model, and you'll actually be able to see the text and the numbers next to it. And the second point, I just thought this is exactly what risk engineers do when they're trying to estimate the damage from an explosion or a fire in the plant. For example, in the chemical plant where I used to work, this is literally what they've done. So this is a hypothetical example about Tom Cruise saving the world, but in reality, the mechanics of it, or the idea behind it, and the decision that it supports, is very real to most operational risks on the planet.
and along those lines, Alex, this idea was suggested by John Button of Gartner. And at first I thought, well, that's a corny idea. As I got into it, it became deeper and deeper. The first thing was defining these ellipses here. Wow, that's complicated stuff, it turns out. And that was the first thing. And then what I'm really going to get to here is let's take a look now. I have a 10% chance, let's say, that the laser on plane 2 will fail, right? There's my 10% chance, right? And remember, if it fails, then I go to the bigger dispersion chart. Well, what would happen if that went to 15%? Oh, then my chance of failure, let me undo, 11% with a 10% chance that the laser fails, 14% chance of failure if there's a 15% chance the laser fails, and you can't do that in your head. But the real thing is, as I started working on this, went through various generations and sent it to my colleague Connor McLemore, who was a naval aviator, as a matter of fact. The whole situation became more interesting, and then I realized we could do something that applied very broadly in the area of Bayesian analysis in this model. And so now I take you to what I call Bayes-o-matic. And the origins of that, none of the audience is old enough to remember this, but on Saturday Night Live years ago, the famous comedian Dan Aykroyd did something called bass-o-matic, where you would simply take a live bass and throw it in a blender and get a blended anyway. So, okay, let me blow it up a little bit more here. And what you're not going to understand what's going on yet. I'm going to do a little lecture on Bayesian analysis when we're done here. But for right now, we're going to say, what is the chance that something in the top row happened, given that whatever is in the bottom row happened? For example, what's the chance that the mission succeeds? 89. We already had that. We had that from the chanceometer at the top. Okay. Yeah, but what's the chance that the mission succeeds given that laser 2 is down? Oh, that's 42.3%. Whoa. So back to your chemical plant, what's the chance that the plant blows up given that the sprinkler system was faulty?
Exactly. This is so powerful to test the effectiveness and the dependency on different controls.
Okay, now let's get to the good part. So notice this. What's the chance that something happens given that the laser is down? Well, it's 100%, of course. So the little dot, the little dashed lines just say we don't care what happened here. But now, what is the chance that the second attack was successful given that the laser was down? And remember, this depends on the skill of the pilot here, right? Because now we got some pilots are better than others, and the laser went, okay. That's 44%. Now I'm going to ask a related but completely different question. I'm going to switch these two, and then you're going to begin to understand the power of Bayesian analysis. Oh, what's the chance? See, I've got what's the chance that the second attack succeeded given that laser 2 was down? And now I'm going to say, what's the chance that laser 2 was down given that we, hit the target. We hit target 2, and that's 4.7%. Wait, why aren't they the same? You're going to see why they're not the same. Okay, let's just talk through it again. One was, if laser 2 is down, what's the chance I'm going to hit this target? The other one is after the fact. I've hit the target. What's the chance that laser 2 was down? It's a complicated computation called Bayesian analysis. And remember, laser 2 only goes down 10% of the time. So if you hit the target, okay, but now I'm going to describe this whole phenomenon in terms of, it's an example I use in my teaching. And so I'm going to use it since I can kind of do it on autopilot. So instead of a mechanical failure here, I want to talk about a medical example. So there is some horrible disease, SHD. And by the way, it is non-communicable. All right? I really should say that. You get it by being hit by a cosmic ray or something. All right? Some horrible communicable. What's the chance I spelled it right and typed it right? So it's really SHND is the proper name for this disease. And I will tell you that it is 1% prevalent. That means 1% of population has it. Okay? That's what prevalent means. Now, luckily, there is a very good test. So accurate test. If your SHND positive, you actually have SHND, then there's a 98% chance you test positive. And drag this down. If your SHND negative, then there's a 98% chance you test negative. And why would you want to get tested? Well, if you catch this, then there's a treatment. Of course, the treatment is so horrible, you probably, wish you were dead anyway, but at least we can treat it, right? So now, but it isn't like you don't want to treat this. It's like rabies shots. You get these horrible, painful shots, and you don't want to just say, "Oh, I think I might have rabies." So here's the question now. this is like a totally random occurrence that you have it. You get hit by a cosmic ray, it does something to a chromosome, and now you have it. So here's the question. What is the chance that you are SHND positive if you test positive, right? So you're in for your annual checkup, they run a test, and the doctor says, wow, you've tested positive for SHND. What do you do? So what is this chance? This is a question for everybody. And if we have people online, it would be very interesting to see. Do we have an online audience today?
We do. Do write your comments in the comment section, and we'll see it here in the studio.
So this is, it is, number one, an important problem. It is, number two, wildly unintuitive. It is, number three, teachable. So when it comes to the bang for the buck for teaching stuff to people, you can't beat this because it is teachable, and I'm going to teach it, and I'm not going to use any algebra. So do we have any guesses here for what is the chance you're actually positive given you got the positive test? Hey, you're muted there, Alex. I don't hear you. Alex, you're muted.
Now?
Yeah, now I hear you. Alex,
Okay.
did you get some responses?
No, I'm saying this could be a very difficult question, so I think we need some hints.
No hints. I'm gonna because
walk us through the solution.
I'm going to walk us through the solution. By the way, I'm going to give you the answer. So remember, if you have the thing, 98% chance you test positive. If you don't have it, 98% chance you test negative. Oh, I tested positive. What's the chance I have it? And a lot of people think 98%. No. The answer is 1/3. So like basically 33%. Okay. Well, now let's walk through this.
And sorry,
Yeah.
before we do that, because this is the concept that Georg Gagarinza in his book Risk Savvy kind of started unraveling, and he's describing what a huge issue this is, not for a hypothetical disease, but for many cancers, where you get a positive result and you start the treatment that sometimes does more damage than if you didn't do it, but also you think you've got a positive test result and that means you have it almost guaranteed, but in fact it's only 33%, which is not enough to make a decision on the treatment until you've done probably more tests, which is what.
Oh, that's absolutely true, Alex. And look, let me tell you some of the results of this. Number one, for men, they like stop doing prostate tests after a while. Because, I mean, even if you test positive, the chance it would make any, yes, this is Max says, this is the base rate fallacy. It's what it's called, right? But they stop doing these prostate tests after you reach a certain age. They say, look, yeah, so what? It's not going to make that much difference. Or mammograms for women after a certain point, the false positives, it's really the false positive problem is going to be the thing that kills us here, right? And so let me now give you the visual version of Bayesian analysis. And we start with, I guess I'm going to start with a think of this as a target. We're going to throw darts at a dartboard, all right? We're throwing darts at this dartboard. And I'm going to create a couple regions in here. So here's a blue region that I'm calling A. And here's a red region I'm calling B. And Bayesian analysis is about the following thing, and it's all it's about. If a dart landed in region A, what's the chance it's also in region B? Or conversely, if the dart landed in region B, what's the chance it's also in region A? So let's do the first one first. So if I am in A, so here let's say so chance of A given B. Is that legible enough? Oh, it's hidden under the ChanceTALK thing. Okay. Chance of A given B. What this means is, you know, let's see if I have a cursor here. Hold on a minute. Can I make a laser pointer? Just a minute. Oh, yeah. Okay. So we know we're in B. So we know we're in this red ellipse. What is the chance that we're in A? Well, duh. We know the dart lies in here. It's just the ratio of the area of this little region in here, which is you're in A and B, right? So let's make sure we write that in there. So this region okay. Hey, it still got me on the laser pointer. Get out of there. That's the laser pointer. I don't want that. I want the pen. Thanks. A and B is that area. So it should be intuitively obvious that the chance of being in these things is proportional to the area. And so the chance of A given B is area of A and B divided by area of A. That's all. And if I wrote this down with probabilities, then it would be Bayes' theorem and it would make your head hurt. So I'm going to just leave it this way. It's just there's a picture. It's just like this part lies in that other part. And so it's just got to be the relative area. Okay, now let's go back to some horrible non-communicable disease. So let's see, I'll erase all the ink. And now I'm going to start out by showing you the entire population of people who could have, this is the population of the world, right? And I'm going to represent it as an area. So that's everybody in the world. Who are the people who have SHND? That's only 1%, remember?
1%. Yes.
So I'm going to draw a little slice down here. And I'm going to do like a little crosshatch. So there, that little slice is 1% who are SHND positive. Those are the people who actually have it. Okay. Now let's talk about the people who test positive. So I'm going to use red here. So red is the people who test. Positive. Well, first of all, we know it's 98% of the people who have it. So I go up here. Come on back. Okay. So I surround this little area. So there's 98% of the 1%. And who else tests positive? Well, remember, if you don't have it, there's a 98% chance that you'll test negative. Oh, but that means there's a 2% chance you'll test positive. Oh, no. So I've got 1% there. Hold on a second. This drawing can get too messy if I don't do something here pretty quick. Well, that's all right. Let me draw this. Okay, let's see if I can erase one thing here. Uh-oh. So, oh my gosh, the controls are suddenly over on the right. Why is that? Okay, let's erase that line. So now remember, go to the laser pointer. So now let's remember, we've got 98% of the people in that thing test positive. And we've got everybody in that, that's 1%, and that's another 1% testing positive. So basically, we have 3% of the population test positive, and yet only 1% of the population has it. So if you test positive, what's the chance you're in the black bar, given that you're in one of these 3 bars? It's 1 in 3. Boom. And this causes no end of problems. In my book on the flaw of averages, oh gosh, yes. So consider the war on terror, all right? And in fact, let me tell you a true story. A former student of mine became a professor at West Point, and was and they were looking. This was during the Iraq War. The Army had developed, they thought, a very accurate test for whether or not a car was carrying a car bomb. And they were all proud of this, and a bunch of PhDs had come up with this method. And this professor I know at West Point had the cadets, as a capstone project, do this kind of analysis where the original analysis didn't even look at the prevalence of car bombs. So there were so few car bombs that even if you thought you detected a car bomb, it was much more likely that it would not be a car bomb, right? Or, you know, in the war on terror, detecting terrorists. Okay, let's go back now to the Top Gun simulation, right?
Let's.
And so how are we doing all this? Well, this is a SITMath model. And as I look at every trial, this was, we hit target 1, we hit target 2, there'd be a 0 otherwise, right? The mission was successful. Laser 1 worked, laser 2 worked. The condition held. The condition is whatever you made up down there, all right? I'll explain that in a second. I'm going to do an entire blog on Bayesian because it is really such a powerful thing you can do with a SITMath model. Oh, and then finally over on the right, I've got condition 1 and 2. So remember, I am interested in the chance that condition 1 happens given the condition 2 happens. What I have to count up are all the 1s in this region. 1 and 2 happens, divided by 2 happens. That's it. So if we look down here, let's see what condition I have. Let's go over here. So, okay, this is a real rare one. Let us say that we hit target 1 given that laser 1 was working. That happened a lot of times, right? Let's go take a look. So we hit target 1. No, okay, that's too much. Let's say that laser 1 was down 66% of the time. Good. Now go over here. So we hit target 1. Oh, here we go. Laser 2 is down, right? Here's laser 2. We hit target 1. Let's go down and look at that again. That was on trial 24. That means that here is condition 1 that we hit target 1. And this is, we hit target 1 and laser 1 is down, right? And so over on this sheet, if you look at this formula, Bayes' rule becomes, oh, sum up all the 1s in condition 1 and 2 and divide by the sum of condition 1, basically, right? And how to do that is also screwy, and I might as well show it here, but we'll have to go into more detail. So when you pull down these little menus, what happens? Well, hold on, let me find out where this points to. Format control, AF47, okay. I've hidden it way over here for now. So if, as you select these things, success, failure, or it doesn't matter, you get the numbers 1 for success, 2 for failure, and 3 for it doesn't matter. Then on the calculations page, what you need to do is string together a bunch of conditions, which are 0s and 1s, and then you have to multiply them all together to say they all happened. So this will be showing this to you now, it would make your eyes glaze over. But I will do a blog on Bayes-O-Matic.
And the good news is that the generator can do this in their sleep.
That what?
The generators can do that in their sleep.
Well, I'm sorry, who can?
Generators.
Oh, yeah. Well, but the thing is, the generators will generate the libraries, which give you the Bayes-O-Matic, and you can do it in your sleep, right?
Exactly.
Oh yeah. No. The eyes glazing over with the yes, exactly. How you set it up. I mean that actually setting it up should be a button in some future version of ChanceTALK Monte Carlo. That's what that should be, right? It is just a simple mechanical process to set this up. And the most, dramatic way to look at this is by reversing these conditions. So the chance that I hit target 1, given that laser 1 is down, see, I could also look at that by disabling laser 1 temporarily, right? Except there's a lot, that also includes all the other things that could have happened when I do that. So if just given the single condition that laser 1 is down, we still have a 66% chance. Why is it 66%? Well, if I disable it, at least I can see the size of the dispersion ellipse over here, right? But now what's interesting is, given that laser 1 was down, what's the chance that you hit target 1? And that's 7%. And again, that's because laser 1 going down is a rare event to begin with, right? So anyway, that's it for today. That's that. Oh, and by the way, going back to an earlier conversation about people not being chance aware, chanceometer.com was available and I took it.
Nice.
And Bayes-O-Matic was available. But you look up Bayes, oh my gosh. A lot of Bayes related URL names are in the $1,000 range.
Wow.
So I think that's it for today. As always,
Thanks, Sam. Thanks, Sam. And I think stay online for just another minute or so. As a backup, I'm saving the video on your computer as well as my computer before it uploads. So I think we should actually have a very good quality video on the replay without any issues with my internet connection. So thank you, everyone. Send through your questions, comments, topics you want us to discuss, and we shall meet very soon to talk about more case studies.